Hello, and welcome to our Wednesday webinar from the International Centre for Sustainable Carbon. My name is Rebecca, and I'm a part of the communications team here. Our monthly webinars are based on our technical reports, which are available from our website, www.sustainable-carbon.org. Residents of member countries and employees of sponsoring organisations can download our reports at no extra charge after our one-off registration on our website. Please type in any questions in the question box as we go along, and we will answer them at the end of the webinar. The subject for today's webinar is rare earth elements, recovery from coal wastes. Over to you, Steve.
Thank you, Rebecca. Hello and welcome to the webinar. Today, as you've just heard, we'll be talking a little bit about rare earth elements, their importance and the potential recovery from certain coal waste. So we'll start the presentation with a brief look at what rare earth elements are, where they're currently produced, and their growing strategic importance in numerous areas of technology. Now, for some years, global rare earth markets have become heavily reliant on Chinese supplies, and there's now a growing incentive to diversify suppliers and find alternative sources. And some types of coal wastes and byproducts are promising candidates. So we'll look at the huge amounts of such waste that are stockpiled around the world, their potential as a source of our REEs, or rare earth elements, and what's being done to develop new techniques capable of their recovery in an economic, sustainable way. And finally, we'll touch on how progress is being made towards commercializing some of the more promising techniques and what the future might hold for this increasingly important group of elements. Now, the rare earth elements comprise 17 metallic elements highlighted on the periodic table here, made of 15 lanthanides plus yttrium and scandium. They fall roughly into three categories, namely light, medium, and heavy rare earth elements. Now, despite their name, these are relatively plentiful in the Earth's crust. For example, if you take cerium, well, it's the 25th most abundant element at an average of 68 parts per million, making it as abundant as copper. The principal economic sources are currently the minerals shown here. However, because of their geochemical properties, rare earth elements don't occur naturally as metallic elements. You generally find them occurring in a range of minerals such as halides, carbonates, oxides and phosphates. And as we'll hear a bit later, this can make the recovery quite challenging. Now, minerals containing rare earths are currently mined mainly in the countries shown here in the table. The latest estimates suggest that global reserves are around 130 million tons or thereabouts, and there's been a steady upward trend in global production, especially over the last decade. In 2013, it was around 100 kilotons, although this had tripled by 2022. Last year, it increased again, reaching 350 kilotons, and output is expected to carry on increasing as demand for these materials continues to escalate. Now, for some years, China's dominated global production of rare earths, with a great deal of production taking place in regions such as Inner Mongolia. But the situation is somewhat different in the USA, for example, which currently has just a single mining operation that now produces around 15% of the world's rare earths. But in contrast, Europe has no operational rare earth mines, or some countries do have reserves. However, there was a significant discovery in 2023 that may change this situation, as Sweden identified what's thought to be the continent's largest rare earth deposit, with resources of more than 1 million tons of oxides. And now the European Union is focusing on developing its own supply chain, and this newly discovered deposit could be crucial in helping meet this aim, although, with a word of caution, it can take many years for new projects such as these to reach full, profitable commercial operation. Now, I'm sure everyone knows why rare earth elements are so important in the modern world. So the main point to take away from this slide is that the global market is not far off doubling between 2021 and 2026, when it could hit $9.6 billion. And China continues to dominate global supply, although many countries are now making moves to reduce their dependence on China as they strive to develop their own more secure supply chains. For example, if partially to reduce its dependence on China, Japan created the Japan Organization for Metals and Energy Security, or JOGMEC. This is an independent administrative institution tasked with resource stockpiling of 34 metals, and that includes rare earths. And through JOGMEC, Japan's continuing to invest in rare earth projects in Australia and other parts of the world. There's a great deal of concern amongst Western nations about China's dominance of the markets, and there are ongoing efforts to counter this. For example, literally a few days ago, the formation of the Mineral Security Partnership was announced. This is a coalition of 14 Western nations that will support the development of critical materials projects, including rare earths. And members at the moment include the USA, Australia, Canada, Estonia, Finland, France, Germany, India, Italy, Japan, and so on. So here are some rather sobering numbers associated with China's current market dominance. China is currently responsible for around 70% of the world's rare earth mining, some 87% of its processing, and 91% of its refining. And this raises clear concerns over cost and security of supply, especially amongst some Western nations. For example, a particular application for certain rare earth elements is in the production of permanent magnets. These are so important for the manufacture of wind turbines and motors for electric vehicles. At the moment, around 94% of these are made in China. Looking to Europe, well, the European Union is an important producer of wind turbines and EV motors. However, current European production is negligible at both the mining and the processing level. Chinese imports meet around 98% of rare earth magnet demand, and the level of imports is set to remain high as the bloc tries to move towards decarbonisation and net zero emissions by mid-century. In addition, China currently manufactures around 23% of the world's wind turbines and 45% of electric vehicles. So it's really no surprise that this situation is causing considerable unease in many developed economies around the world. Now, China's dominance in global production has come at a significant environmental cost to parts of the country. For many years, China relied on really notoriously polluting extraction methods that released huge quantities of contaminated water and other chemicals into the environment. Chinese rare earths are produced from mineral sources, mainly through two methods. One involves the removal of topsoil and its transfer to leaching ponds, where acids and other chemicals are used to start the separation of rare earths from mixed clays, soil and rock and so on. Or alternatively, it relies on what's known as in situ leaching, with the resultant mixture then pumped directly to leaching ponds for further separation treatment. Now, all of these methods produce considerable quantities of waste. As you can see on the slide here, some estimates suggest the production of 1 ton of rare earth elements can generate the amounts of pollutants and unwanted materials shown here, and that production of every ton of rare earths creates on average 2,000 tons of toxic waste. Now, it wasn't until 2016 that stricter regulations governing rare earth mining were introduced in China, although by then significant environmental damage had occurred because of factors such as disruption caused by mining operations, surface erosion, and toxic leaks from leaching ponds. China's current dominance of the global rare earth markets may be partly due to lax environmental regulations. Low cost and high pollution methods enable the country to undercut many competitors and create a strong foothold in international markets, although at a considerable environmental cost. Now, this slide is just to give you some idea of the type and scale of Chinese operations. The largest rare earth element mine in the world is Bayan-Obo in China. This has a huge tailing pond, and there are over 70,000 tons of radioactive thorium-containing waste stored in the area. The pond lacks a proper lining, and the contents are seeping into groundwater that will eventually reach the Yellow River, a key source of drinking water. And there are thought to be numerous similarly unsafe sites throughout China. So what's being done to find new sources of rare earth elements around the world? Well, several main avenues are being followed. There's harvesting as yet untapped natural sources, such as mineral ores. There's also the possibility of recovery from some industrial wastes, such as phosphate mining wastes, bauxite residue from aluminium production, metallurgical slags, and some electronic wastes. And of course, there's also the possibility of recovery from coal, coal wastes and byproducts. And here are some of the examples of major developments taking place in different countries. Let's look at Sweden. Well, in 2023, the state-owned company LKAB identified Europe's largest rare earth deposit in Kiruna in Lapland, with resources thought to be of more than 1 million tons of rare earth oxides. This newly discovered deposit could be crucial to Europe, which currently, as you've heard, has no rare earth mines in operation, although the EU is intent on developing its own supply chain. Europe's demand for rare earth elements is expected to rise 5-fold by 2030. However, it could take some years before the Swedish mine becomes fully operational. And turning to Poland, well, a rare earth separation plant is being developed by a Canadian minerals company partnered with a major Polish chemicals company at the moment. The new plant will be supplied with rare earth carbonates from a deposit in Malawi in Africa, but will also be available to process materials from third parties. There's also growing interest in Poland in extracting rare earths from coal waste, which I'll talk about a little later. Poland has a long history of relying on coal for almost all of its power generation, and it's accumulated huge quantities of power plant ash in particular, and around 20 million tonnes continues to be added each year. It's been determined that some of these ashes contain significant levels of rare earths, and the Polish Institute of Mining Technology has been investigating the levels in mine waste from dumps and flotation tailings ponds. Initial work looks promising, and the rare earth levels in some types could make it economically viable. And in South Africa, several potential routes are being followed. Some of them are concentrating on mineral sources, but there's also growing interest in the potential use of run-of-mine coal and coal discard produced from coal cleaning operations. And these have been the focus of studies carried out by the University of Witwatersrand. Their works determine that total rare earth element content in both of these could be enough to make their recovery economically viable. Now, moving to Australia. Well, the country's got significant proven reserves of rare earth, and in 2022 produced around 18,000 tonnes. There's a goal to boost production capacity, and efforts are underway to locate and capitalise on several new, as yet untapped deposits. And as part of this drive, in January of this year, the Australian government said it would invest heavily into rare earth and critical mineral research as part of its efforts really to become a major global supplier. And there are a number of important projects at various stages that include those shown here on the slide. So far, most industry initiatives have been concentrating on increasing production from conventional mineral sources. Also, there's also growing interest in recovering rare earth from power plant ash, as some of these have been found to contain fairly high levels. And work's also underway in Canada, where the University of British Columbia has found that some bituminous coals and some lignites contain significant levels of rare earths, making them promising viable candidates. Now, given the drawbacks such as cost, complexity, environmental impact, and security of supply associated with producing rare earths from conventional mineral sources, there's a clear and obvious incentive to diversify suppliers and find alternative sources. As we've mentioned, one potential major group is made up of different types of coal and coal waste and byproducts. Now, most countries with a history of using coal for power generation and industrial applications will have legacy dumps consisting of combinations of combustion ash and waste materials from mining activities, along with waste from coal preparation plants and so on. Some of these materials can contain quite significant amounts of rare earths, but a major drawback is that data on the makeup and volume of individual dumps is often lacking. This can be further complicated by the fact that the amounts of rare earth elements present can vary widely between and indeed within deposits. So identifying the best deposits will be important, as it would clearly be a pointless exercise to process those with low levels. Now, even though coal use has declined in some parts of the world, its importance as a fuel for power generation continues, especially in Asia. Annual global coal consumption now exceeds 8 gigatons. And this level of use generates more than 1 gigaton each year of fly ash alone. And as has been well established, some fly ash can can contain significant amounts of rare earths. And here are a few examples of the current situation from around the world. So looking at China, for example, well, the country generates more than 600 million tons a year of ash, of which about 70% is processed into various industrial products. But much of the balance is deposited in around 3,000 large dumps that occupy at least 20,000 hectares. Statistics are incomplete, and it's unclear just how much waste has been stockpiled over the years, but it may now be well in excess of 6 gigatons. So, around the world, there are huge quantities of these types of materials, some at least with the potential of becoming viable sources of rare earths. Now, clearly we don't have time to go through each of these points, but for example, using coal-based materials would reduce the need for new rare earth mines, thereby avoiding the associated environmental damage that historically has been a characteristic of this type of activity. Also, it may take a long time to get a new rare earth mine up and running. I mentioned earlier the recently discovered large deposit in Sweden. Some industry sources think it could take up to 15 years before this reaches full operation, whereas developing processes to recover rare earths from some coal waste could be quite fast. Around 4 years has been suggested for some. On the environmental front, as well as avoiding disruption associated with developing new mines, recovery of rare earths from historical waste dumps can simultaneously help reduce environmental impacts, such as acid runoff and land erosion, effectively turning what's a liability into a useful resource. And of course, recovering rare earth elements from various coal waste would make use of an indigenous resource, and that would help minimize reliance on imported supplies, improve national security of supply, and at the same time, helping keep up momentum of the green transition, all major drivers behind current programs. So even though the development of most rare earth recovery techniques based on coal-derived materials will face technical and indeed environmental and economic challenges, the world has already amassed huge amounts of these potentially valuable resources. Given the current situation where the global market is dominated by one major supplier, there are clear incentives for pursuing the development of sustainable processes capable of recovering rare earths from these coal-based materials. Now, as we just heard, fly ash is often available in huge quantities. It's generally a fine-grained solid containing both amorphous and crystalline phases, derived from both non-combustible constituents of coal, such as clay minerals and quartz and so on. And when coal's burned, rare earth compounds become concentrated in the ash, with up to possibly 40% or thereabouts ending up in the glassy fraction that's formed. So they're found in higher concentrations than that of the original coal. This can be about 8 to 10-fold higher. However, one drawback is the composition of fly ash can be highly variable. But it's been determined that the global average of rare elements in coal ash is around 400 ppm, and that's greater than some mineral sources. And some ashes have been found to contain reasonably high levels of the more valuable, heavier rare earth elements, something that could help the economics of a particular process. For example, some Chinese ash has been found to contain on average about 8% heavy rare earths, those from South Korea around 6.4%, and those from India around 5%. Very large amounts of fly ash are readily available in parts of the world, so research into recovering them is ongoing in a number of countries, such as the one shown here, and indeed many more. Some countries do have ash resources that show potential, although the lower levels in others is likely to rule them out as being uneconomic, although most countries will have at least one source of ash with average rare earth concentration above the global average. So it'll be important to identify and concentrate recovery on ashes with the highest concentrations. Now, a wide range of potential recovery techniques have been proposed, developed, or trialed. Some have proved to be more promising than others. So far, many processes have relied on various forms of acid or alkali leaching, followed by multiple downstream cleanup and separation stages. A number of factors can influence rare earth recovery from fly ash and other coal residues when using leaching techniques. And these, for instance, include the mineralogy of the particular ash, how the rare earths present are encapsulated in the ash, the overall grain size of the material, and the presence of competing materials, and these can cause complications with some downstream processing stages. And of course, economic factors in particular come into play with larger scale leaching. And these are influenced by factors such as capital and operating costs for the particular process, leaching recovery rate, plus any environmental impacts that might result. All such aspects, and often others, need to be considered when pursuing a possible recovery technique. Now, although investigations into extracting rare earths from coal waste and other byproducts have been underway for some years, it still remains something of an emerging field. Numerous processes have been proposed during the past decade or so, some of which are now moving towards considerable scaling up, with the hope of eventually reaching full-scale deployment. So several appear to be close to this commercial operation stage, although none have yet reached this. Conventional recovery processes are usually based on chemical leaching, where materials are dissolved in acids or alkaline solutions, releasing the rare earths along with other metals. Sequential processing stages are then required, often producing toxic wastes that require appropriate treatment. However, using coal-based materials may provide some advantages over conventional rare earth recovery. So, as well as chemical recovery methods, various physical separation techniques have also been used, such as these shown on the slide. Some proposed recovery schemes combine a physical separation stage with a further downstream chemical processing. These aim to make subsequent rare earth recovery easier and more effective. Various techniques have been proposed or evaluated, such as alkaline and thermal pretreatment, roasting, microwaves, and plasma treatment. And many of these techniques are discussed in the report that we'll be talking about in a moment. Overall, there are many techniques for recovering rare earths being developed and evaluated around the world, many comprising different combinations of physical separation with pre-treatment, followed by chemical-based extraction and recovery. But alongside these, there are also several novel processes that help to achieve rare earth recovery that doesn't rely on the use of strong acids or alkalis, or require multiple sequential extraction phases. They hope to be simpler, more cost-effective, and less environmentally challenging. So, numerous techniques continue to be proposed or trialed with a view to eventually achieving viable commercial rare earth recovery within quite a number of countries. Excuse me. I'm currently finalizing a report that's looking into various aspects of rare earth recovery from coal-based materials and their potential for helping meet the growing global demand. My report will be republished in the next few months and reviews the potential of a range of techniques that appear to show promise, either in terms of reducing capital or operating costs, increasing recovery yields, minimizing or avoiding the need for strong acids, alkalis, and various other toxic chemicals that often form part of a recovery scheme, and minimizing environmental impact to land, air, and groundwater. As we've already mentioned, numerous techniques have been proposed or are currently being tested or in the process of being scaled up. And amongst these, there are a number of systems that appear to show promise in meeting these aims. The report looks at some of these that include those shown here on the slide. Now, although some of these look promising, work has often so far been limited largely to laboratory scale, so their effectiveness still needs to be validated at larger scale. Some of them still lack firm data on their economic viability and possible environmental impact when scaled up. This will be needed as part of any process hoping to eventually reach commercial operations. Some processes have progressed further than others and are or have been tested at pilot scale. But many proposed systems will still need further work to confirm they can provide an effective, cost-effective means for recovering rare earth elements if they're to reach full commercialization. Now, projects looking into the potential of coal-based materials as viable sources of rare earths are underway in many countries, but the biggest program by far has been underway for some years in the USA. For the past decade or so, the Department of Energy has been investing heavily to develop potentially sustainable domestic sources of rare earths from coal and coal waste products. NETL or NETL is leading national research efforts to help secure supplies from US resources and potentially help supply global markets. And ongoing projects include work to characterize rare earths present in various coal-based materials, acid mine drainage treatment sludge, and young lignites from North Dakota and elsewhere. Since 2014, the Department of Energy, Office of Fuel Energy, and NETL have been engaged in a program of research, development, and demonstration, focusing on all aspects such as extraction, separation, recovery, and purification of rare earth elements and other critical minerals from coal-based resources. Numerous US private sector organizations and academia are engaged in a range of projects with the overarching aim of finding ways with practical, viable technologies capable of maximizing resource development and recovery, such as the importance of rare earth elements in modern economies. So, as I've just mentioned, many processes have only been evaluated at a limited scale, although efforts are underway, mainly in the USA, to drive selected options forward to larger scale commercial operation. Many of these have their roots in NETL's what's termed the Rare Earth Elements from Coal and Coal Byproducts RD&D program. And as part of this, NETL has been supporting the development of several pilot scale facilities capable of producing mixed rare earth oxides from coal products. A range of organizations, including US universities with Department of Energy funding and private sector organizations, are working on such projects, with a number of possible recovery routes and techniques being evaluated at pilot scale. Several appear to be making headway and are progressing towards the ultimate aim of reaching commercialization. And the table here shows examples of the type and scale of some pilot scale projects at various stages in their development. As you can see, these projects are looking at a range of materials that include lignite, coal waste, acid mine drainage and its associated sludge, mine tailings, and power plant ash. So where are we headed? Where do we go from here? Now, when it comes to rare earth elements, there are well-documented global supply constraints. Much of the developed world continues to rely heavily on China, with all the attendant risks that carries. These materials are vital for numerous high-tech applications, some crucially important as part of global efforts to counter climate change and move towards net zero emissions. And their importance is only likely to increase as further technological developments in the field continue to be made. So, largely because of concerns over a combination of economics, environmental impacts, and security of supply, it's become increasingly important to find new sources. And one family of materials that holds great potential is coal-based materials. Many developed economies have huge legacy stockpiles of waste, often accumulated over a century or more of coal use, and some of these materials contain reasonable concentrations of rare earth elements, hence ongoing efforts to capitalize them as a viable domestic source. Recovering rare earths from these materials could provide significant economic and environmental benefits, at the same time minimizing dependence on potentially unreliable outside sources, often at the mercy of unforeseen geopolitical developments. Many types of research have been conducted into this important issue, and efforts to recover rare earths from coal and coal materials remains an ongoing project in many countries. So far, numerous techniques have been proposed or trialed with varying degrees of success. Many of these have been technically successful at a small scale, but when it comes to scaling up and achieving sustainable, cost-effective operation on a commercial scale, some still lack robust examination in terms of their economic potential and in some cases their environmental impact. So there's more to be done. Many proposed recovery systems will face considerable challenges in achieving this, although progress is being made along several possible pathways to industrial scale applications. And we've touched on a few of these today. Some projects have reached pilot scale, several are moving towards commercialization, although in some cases there's still uncertainty over timescales involved to reach this stage. Doubtless, there will still be difficulties ahead for commercializing rare earth recovery from coal-based materials. Many proposed processes will be economically and environmentally challenging, to say the least, and finding the right balance between efficiency, cost, and environmental impact will be crucial. However, having said that, this is a rapidly evolving field, and current and future developments will hopefully arrive at a place that will allow coal and its associated waste to become viable, sustainable, secure sources of rare earth elements, materials vital for so many applications. And to close, the potential rewards are huge. Well, thank you very much for your attention. We'll see if we have any questions have come in. We have one here so far. What type of coal material can be considered as a potential source of rare earth elements? Is there any particular coal characteristics that are important? Well, looking at coals themselves rather than waste, well, the global average rare earth content of lignite, for instance, is around 70 parts per million. But when it's been burned and in its ash form, it's nearer 400 ppm. And for bituminous coal, it's around 70 and 470 ppm. So that's the global average. But having said that, levels can be much higher in some cases. For instance, if you look at fly ashes from some Chinese power plants, they can be between 700 and nearly 2,500 ppm of rare earth elements. There are also rare earth elements in bottom ash from power plants, but fly ash tends to be higher. Now, in terms of what gives a particular coal potential as a source of rare earth, that really depends on a whole host of factors, such as the physical and chemical properties of that particular coal. For example, some studies have suggested that about a quarter of the rare earths in a coal are associated with organic matter. And of course, that can influence what extraction methods might be used downstream. And indeed, rare earth extraction from some younger coals, such as lignites and some bituminous coals, have been shown to be easier, partially because as a result of their chemical and physical makeup. Some are easier to dissolve, making rare earth recovery much easier. But often it will be a case of assessing and testing a particular source of coal for its suitability. Rare earth contents can vary very widely between individual seams and indeed within them. And of course, another possibility is we haven't really touched on much today is acid mine drainage from mining operations. This is this acidic water-based runoff that someone is just asking a question about a second. How long do the impacts of acid mine drainage last for? Is it fairly short term, or can it continue for a long time? Well, acid mine drainage, or AMD as it's generally abbreviated to, it's still an environmental problem in many parts of the world. Even after all mining operations and so on have ended, contaminated water can still leak out of old workings for many years, and of course, it invariably finds its way into streams and groundwater that could be a source of drinking water. And apart from that, it can have quite severe environmental impacts on local flora and fauna, for instance. AMD clearly tends to be a bigger problem in countries with a history of coal production. If you take the USA, for instance, there are thought to be around 20,000 kilometers of waterways that have been affected by contamination from AMD. And some of these have been particularly heavily impacted, such as the abandoned coal mining area in the Midwest region. So to answer your question, yes, unless it's tackled its source, impacts of AMD can continue almost indefinitely. And that's one reason why they have potential as a useful source of rare earth elements. It could potentially become a useful resource rather than an environmental problem, which it is in many places now. What about the processing technology? Yeah, someone has asked about what about the processing technology? Even if one were to extract rare earth from coal ash, China is still needed for the processing. Is anything being done with processing capacity in Europe or the US? Yep. Yes, the report will look into this in some detail, but you're quite correct. Most of the downstream processing and separation is carried out in China. Even the one operational rare earth mine in the USA, Mountain Pass, produces mixed rare earths, but these are then shipped to China for processing, which is something obviously the American government is not happy about. And this is the case from many other sources, mostly shipped to China for downstream processing. There are efforts underway in the US in particular with a view to this, and several major projects are being built at the moment, and I think one has actually started small-scale operation for separation. And again, these are talked about in some detail in my upcoming report. And in Europe, there's one small separation plant in Estonia, but there are plans to increase capacity in other areas of Europe, although it's very much at the early stage at the moment. But clearly, it's not just a case of producing the rare earth elements from the ground, as you say. It's the actual downstream processing which is important, and at the moment, China has a handle on most of that. Nicholas Wagner has just commented, for confirmation, there is as yet no commercial demonstration plant in operation. That's correct. There are several that are, well, there are a number of small-scale demonstration plants, I suppose you call them, but they're really pilot-scale operations. And there are several projects in the US that have now gone slightly beyond that and are moving to sort of limited, I would say, small-scale commercial operation. Although those are really at the stage of being built and commissioned at the moment, so there isn't actually much output from them. But excuse me, that's a problem at the moment until those become operational and produce some hard data, which is going to be necessary for scaling them up even further and even developing new plants, obviously, in the longer term. But that will be absolutely crucial to breaking China's stranglehold on the market. Well, that seems to be all the questions. Thank you very much. So I can say thank you again for listening. I hope some of this has been useful. And if anyone wants to make contact directly, please email me and I'll try to answer your questions. So I'll hand you back to Rebecca now. Thank you for your attention.
Thank you very much, Steve. The only thing I have to say is the slides from this webinar will be available to download from our webinar page of our website shortly. Thank you all for joining us today, and goodbye.